Eye Joe, I've been married a long time ago. Where did you come from? Where did you go? Where did you come from, Cotton Eye Joe? If it hadn't been for Cotton Eye Joe, I've been married a long time ago. Where did you come from? Where did you go? Where did you come from, Cotton Eye Joe?
Alright, I hope that you guys found that cool. The glowing pickle, you put the electrodes, those two metal rods, through the pickle, and then you run an electric current through it. You do need to be careful if you try that at home. I just took a little part of a YouTube video. The pickles can explode, okay, and so it's very dangerous, which is why we won't be making pickles glow, but we will still be, on Monday, we will be making fruit veggie clocks, one or the other, okay? Alright, so this is 15.3, okay? 15.3, we're talking now not about homogeneous mixtures, but heterogeneous mixtures. So turn in your books to page 459 and make sure you are adding to your notes, highlighting things, so that way you have this information to help you on your test. Okay? 15.3 was pretty different from our homogeneous, because now we're not working with aqueous solutions, we are working with the odd solutions, okay? Things that are thick, and they don't really seem like liquid, but they are, based on their properties, okay? Or at least for our chemistry class, they are. Okay, so in our 15.3, we start with a suspension. So suspensions are similar to our solutions, but they are different, okay? So we're still dealing with aqueous systems, but our suspensions deal with larger particles, okay? And so these large particles don't stay in suspension. They don't stay in their solution. So you're going to eventually have them separate out, so you can see two different layers, like with milk. If you let milk sit in the fridge, or even outside of the fridge, for too long, then it starts to get this clearishy, maybe yellow liquid on top, and this really thick whitish substance at the bottom. That's because eventually those milk particles came out of suspension. So the lighter liquid particles stay up top, and the heavier, denser ones fall to the bottom. And then it smells, and it's disgusting, nasty curdled milk. Ugh. Just pitch that milk before it gets there. So that's our suspension. Suspensions are larger. With our heterogeneous solutions, you can tell that it's heterogeneous because you can pick at least two parts out of the solution. You can see that they are different. Where homogeneous, like we mixed our salt water, you couldn't tell that there were salt particles in our solution, okay, once they had all been dissolved. Heterogeneous, you will always be able to pull out a difference of particles, okay? And so that is page 459, suspensions. We're going to go ahead and keep moving, and we're going to talk about colloids. Okay, so our colloids, as you can see on page 460, these particles are smaller than our suspensions, but still bigger than our solutions, okay, the solutes. And so these ones, again, you're going to be able to, maybe they look a little more mixed. You can't pull out the different points, but eventually they will fall out of solution. Examples of colloids are egg whites, and like in mayonnaise. Mayonnaise is a colloid. Jellies, okay, things like that. Eventually, those parts will come out. And if you were to shine a light through those, which we'll practice that on Monday, hopefully, maybe even Friday, when you shine a light through them, it's going to not send the beam completely through, because the light hits the particles in the solution, and then it gets diffracted, okay? It gets sent in different directions, so you won't have it continue through your whole solution, okay? Kind of cool for a colloid. Alright, so I want to show you the Brownian motion. Okay, this is when you're flashing the light through colloids. The particles kind of react strangely, and so that movement is very chaotic and random, and this is light shown on red algae. And then our next video will shine that light through another substance, but still Brownian motion. So you can see those particles just kind of randomly moving. The dark shadows going through shows that this solution is deeper than one cell. Okay, and so they'll move through. Okay, kind of cool. And so then this is Brownian's movement through the tiny, tiny particles of water. And so those particles start to reflect light. It looks like glowing little white circular atoms. And that's actually the light reflecting off of those moving particles, okay? Which again, is pretty cool. So you've seen Brownian motion. That Brownian motion is from the Tyndall effect, which we said, that light beam going through our colloid substances, they're going to scatter the light. That's the Tyndall effect, and you see that in the Brownian motion, okay? I'd also like to discuss coagulation and how that relates to us, okay? Everybody should know their blood type. And the way that we do that, and we'll do this in anatomy, you should take anatomy. It's the best. Almost as good as chemistry. Maybe the same. Anyways, I'm biased. Coagulation, when we need to tell your blood type, we will take a sample of blood, and then we add some antibodies to it. Okay, this antibody or anti-serum will cause the blood to coagulate. It clumps, okay? And that way we can tell, okay, if it clumps, it is this blood type, not this blood type, because the anti-serum helps to kind of give you the code, as it will only react with one blood type or another, okay? And that's how we get whether we're A or B or O or AB, and whether we're positive or negative blood types. So coagulation is pretty cool. Alright, and then our last little bit is over emulsions. With emulsions, the example of the emulsion would be mayonnaise, okay, and it gives you that on page 462, which is where we're at. So our emulsion is a colloid dispersion, okay, a colloid that is a liquid within a liquid, okay, so combining two liquids together, but then it forms a colloid. So normally you would have, like in the example of mayonnaise, it tells us, oh, and I just had it, you have vinegar and oil. And so like with salad dressing, vinegar and oil, you'll mix them together, but as soon as you leave them, let them sit, then they separate into those two layers of vinegar and oil. But if you add an emulsifying agent, like eggs, then it will keep the vinegar and the oil in that solution. And so you'll have this white emulsion of mayonnaise, okay, which is kind of gross, but delicious maybe on sandwiches and in tuna fish, and I don't know. Please don't eat it plain. Okay. But anyways, that is dealing with 15.3. Pretty quick, I think. But if you have any questions at all, okay, know that I'm not right there with you, okay, even though my head's talking on your screen. But please email me or add a comment and on Edmodo, and that way I can give you pretty quick feedback, and you don't have to wait until our next class to get your answer. Okay. One last thing, just to kind of go over all this together, I have a visual for us. I like visuals. Okay. Oops. Sorry. I've got a ping pong, this orange one. I have a foam ball. Okay, which is a little bit smaller than a baseball, but that's the size we're going for. And then a basketball. Okay, so if I give you these three size particles, which one would be our colloid? Which one would be our suspension? And which one would be our solvent? Okay, And I would like for you to put your answers here on the side. Or is it here? Okay, so hopefully in your answer, and I'm going to go ahead and put these down before I hit something or, I don't know, break something. Okay, hopefully you guys started to think about the particles and maybe like a sieve, okay? If I gave you a sieve or a filter that was the size of a basketball hoop, okay? If you put your hands in front of you and kind of make a circle touching your elbows, it's pretty close to a basketball hoop, okay? Maybe for most of us. Which would pass through? Would our three particles, would our ping pong pass through? Would our baseball, foam ball pass through? Or would our basketball pass through the sieve, okay? And if everything's passing through, are we really filtering? Okay, there's another thought. I'd want to remind you though that particles, yes, these are huge. It gives you a visual, but most particles are less than 1 nanometer in diameter. I have nothing in here that is a good example of a nanometer. Okay, it's too small for me to show you. Where colloid particles are 10 to 1,000 times larger than those of individual particles, like in solutions, solvents, and those of suspensions exceed even the largest particle, like our. So hopefully you had our basketball as the suspension, our foam ball baseball as the colloid, and our ping pong ball as the particles or solvent solution particles. Okay, I hope that helps. Again, email me if you have any questions. All right, see you guys later.